Hello students, and welcome back to another geometry video. You know what to do. Pause the video, answer these questions in your notes. Do what you can, even if you don't know the answer to them. Give them your best shot, and then unpause the video, and we'll talk a bit. So, this video starts Chapter 9, and Chapter 9 is all about right triangles. So, the Pythagorean Theorem, maybe you've heard of it, maybe you haven't. A squared plus b squared equals c squared. That's what it is. When can you use it? With right triangles. That's why Chapter 9 is all about right triangles, and we're going to start with the Pythagorean Theorem. So, can you write the Pythagorean Theorem as an if-then statement? Remember, Chapter 2 are conditional statements. If what, then what? And then, once you write an if-then statement, can you write the converse of that if-then statement? Can you write the converse of the Pythagorean Theorem? Now, we're not going to do this right now because that's what section 9.1 is about. We're going to learn about the Pythagorean Theorem and its converse, but I want you to get started thinking about these. See if you can write it yourself before we even talk about it together. So, without further ado, let's get in to Chapter 9, first section 9.1. And it is about the Pythagorean Theorem. So, our learning target today is, you know what the Pythagorean Theorem says. What is the Pythagorean Theorem? When can you use it? If what, then what? And our success criteria is that you can use the Pythagorean Theorem to solve problems. This pattern from Chapter 8 continues that we need to know what the theorem says, we need to be able to use the theorem. So, we're going to need some vocab to start off Chapter 9. So, the hypotenuse. Maybe you've heard this word before, maybe you haven't. What is a hypotenuse? And that's how you say this word. It is the side opposite of the right angle in a right triangle. Opposite the right angle. So if we go to the box, right, the red box in the corner, which means right angle, if we draw a line away from it, it's the side that is opposite the right angle. The sides that are attached to the right angle are called legs. The sides that are perpendicular to one another, those are called legs. Two legs, one hypotenuse. So, the hypotenuse is opposite the right angle. It's also the longest side. The longest side of the triangle. Now, that's not the definition. If it's the longest side of the triangle, oh, that's the hypotenuse. No. It just so happens that the hypotenuse is the longest side of the triangle. Because 90 degrees is the biggest angle in this triangle. Remember section 6.5? The bigger the angles, the bigger the opposite side is. So, that's a result of section 6.5. And if you want that, I'll put a link to the description, or a link to that video in the description, because why not? Alright, those are actually all the vocab words we need to jump right in to the Pythagorean Theorem. So, in a right triangle, the square of the length of the hypotenuse, so that's c is our hypotenuse, and the square, so c squared, is equal to the sum, remember sum means we're adding things together, the sum of the squares of the lengths of the legs. So A and B are the legs, or the lengths of the legs. We're going to square them and add them together. So c squared equals a squared plus b squared. You can also rewrite this as a squared plus b squared equals c squared. It's whatever you're comfortable with. But in a right triangle, if we have a right triangle, then the Pythagorean Theorem is true. If we don't have a right triangle, does the Pythagorean Theorem work? I don't know. So we're only going to use it when we see a right triangle. Okay, let's see some more important information, or more vocab, about the Pythagorean theorem. A Pythagorean triple. Pythagorean triple. When you hear triple, you think 3. So a Pythagorean theorem, or excuse me, a Pythagorean triple is a set of 3 positive integers, a, b, and c, that satisfy the Pythagorean theorem. So if you have 3 numbers that you can plug them into a squared plus b squared equals c squared, and you get a true statement, those are Pythagorean triples. So some of the most common, maybe you've heard of a 3, 4, 5 triangle. If you know you have a right triangle, and you know one side is 5, one side is 4, oh, you know it's a 3, 4, 5 triangle. If you know the legs are 3 and 4, oh, you know the hypotenuse is 5. So that's probably the most common right triangle, is called a 3, 4, 5 triangle, because the sides are 3, 4, and 5. And if you take a 3, 4, 5 triangle and you multiply it, right? So 3, 4, 5. If you multiply all the sides by 2, then we get a 6, 8, 10 triangle. That's still a Pythagorean triple. So this is just if you multiply by 2, if you multiply by 3, and etc., etc. You take 3 times some number, 4 times that number, and 5 times that number, and you'll get another Pythagorean triple. So any multiple of 3, 4, and 5 will give you another right triangle. More Pythagorean triples. 5, 12, and 13 also work. 5 squared plus 12 squared equals 13 squared. That's what these triples mean. These triples mean 8 squared plus 15 squared equals 17 squared. And you can check all of these, right, with your calculator. Plug it in, and you can check. And any multiple of 5, 12, and 13 is also a Pythagorean triple. So, the most common Pythagorean triples are in bold up here at the top. The other triples are the result of multiplying each integer in boldface, each integer in a boldface triple by the same factor. Gotta be by the same factor, right? We multiplied by 2 on all the sides, so gotta multiply by 2 on all the sides, but yes. And this is because the reason that we still get a Pythagorean triple is because the triangles are similar. Oh, remember from chapter 8, remember 8.3, if the sides are proportional, then the triangles are similar. So that's, we know we still have a right triangle and all that jazz if we multiply by all of the sides by 2. Okay, so that's what a Pythagorean triple is and how they connect with the Pythagorean theorem. Now, let's do our first example using the Pythagorean theorem. We want to find the value of x, and then we want to tell whether the side lengths form a Pythagorean triple. So there's 2 parts to this question. First, we want to find the value of x, and then we want to tell whether the side lengths form a Pythagorean triple. So, we have that the legs, right, the side opposite the right angle is the hypotenuse, and so x is the hypotenuse. You don't have to label the hypotenuse, but I think it's helpful. I think it's very helpful. So, we know that a squared plus b squared equals c squared. Now, c is always the hypotenuse. Always. You have something squared plus something squared. These are the legs. And whatever you're equal to, a squared plus b squared equals c squared, that is always the hypotenuse. Now this could be c, this could be x, it could be q, whatever you want. But whatever is alone on one side of the equal sign, that is the hypotenuse, and whatever you're adding together on the other side of the equal sign, those are the legs. So that's why I like to label my diagram. The sides that are perpendicular to each other, the ones that make the right angle, those are legs, and the side opposite the right angle is the hypotenuse. So now I know that I can say 5 squared plus 12 squared equals x squared. Take the legs, 5 and 12, square them, and add them together. A squared plus b squared equals hypotenuse squared. Leg squared plus leg squared equals hypotenuse squared. Now some people ask me, wait a minute, I did 12 squared plus 5 squared equals x squared. Did I do it wrong? No, you did not do it wrong. 3 plus 5 is the same thing as 5 plus 3. So it doesn't matter if 5 is the first leg or if 12 is the first leg. It doesn't matter. As long as the hypotenuse is all by itself on one side of the equal sign, that is what is important. Excuse me. Okay. So, beautiful. This equation is going to take us home. It's going to help us finish the problem. 5 squared plus 12 squared equals x squared. Let's take 5 squared is 25 plus 12 squared is 144 equals x squared. Now, 25 plus 144 is 169. So I just added 25 plus 144 equals 169. So that is equal to x squared. And now, this is not x, right? I wanted to find the value of x. In the end, I want x equals some number. But I don't have x equals some number. I have x squared equals some number. So how can I get rid of this square? Well, I can take the square root of both sides. That cancels out the square with the x. And what is the square root of 169? Is 13. Now some of you might say, wait, isn't it plus or minus 13? Technically, yes, but we're talking about the side of a triangle. I can't have negative 13 inches on the side of a triangle. That doesn't make any sense. It has to be positive 13 when we're talking about lengths, because I can't have a negative length. What would it mean if I told you this pen was negative 5 inches long? What does that mean? So, positive. We're going to take the positive. Okay, wonderful. We found the value of x. Part 1 is done. Part 2 says, tell whether the side lengths form a Pythagorean triple. Well, if I have a Pythagorean triple, that means I should be able to say 5 squared plus 12 squared equals 13 squared. Can I do that? Does 25 plus 144 equal 169? Yes. Yes, they do. So because a squared plus b squared equals c squared, these sides form a Pythagorean triple. So we would say, yes, they form a Pythagorean triple. And if you'll remember from our last slide, the common Pythagorean triples, 5, 12, and 13 was one of the common Pythagorean triples. And we have 5, 12, and 13. So that's another way that we could check. And another way we can check is by scrolling to the next slide. Find the value of x. X equals 13. Because the side lengths 5, 12, and 13 are integers that satisfy the equation, c squared equals a squared plus b squared, they form a Pythagorean triple. So, We were right. Woohoo! Let's move on to another example. In the last problem, I told you what the legs were, and you had to find the hypotenuse. In this example, we know what the hypotenuse is, but one of the legs is x. One of the legs is missing. I don't know what it is. So, again, two parts to this problem. First, find the value of x. Second, tell whether the side lengths form a Pythagorean triple. So, now we still have a squared plus b squared equals c squared. But now things look a little bit different because I know, so 14 is my hypotenuse. This is my hypotenuse, whoops. Hypotenuse, which means it is c. The hypotenuse is c. And then I can make, it doesn't matter, a can be 7, x can be b, or we can switch these. It doesn't matter, however you want to do it. So, we know that the hypotenuse is c, and we know that the legs are a and b. So, now let's plug these in. A is 7, so we have 7 squared, plus b is x, plus x squared, equals c squared, or the hypotenuse, 14 squared. Now, I can square things. 7 squared is 49, plus x squared equals 14 squared is 196. Now, this isn't like last time. The x squared isn't by itself. I cannot take the square root yet. I need to get the x squared by itself. So, we're going to move the 49 over to the other side of the equation. Subtract 49 from both sides. And we get x squared equals 196 minus 49 is 147. Now I can take the square root. So that gets rid of the square on the x. And x equals, wait a minute. Can I find the square root of 147 nicely? I get some big long decimal. Now, sometimes the big long decimal is okay, but there's a difference between finding the exact side length and finding an approximate side length. If I give you the big long decimal, 12.12435, blah, 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 that is an approximate answer. We have to use the squiggly equal sign, which means approximate, and it's not an exact answer. Sometimes that's okay. Sometimes we want an exact answer, which means that we're going to take x equals the square root of 147. This is the exact answer. But can we simplify this at all? Like, so for example, if you ever got an answer of 2/3, well, 2/3 is approximately 0.6666 repeating. But that's not an exact answer. If you told me 0.66666, that's not an exact answer. 2/3 is the exact answer. But you can simplify fractions. In the same way that we can simplify fractions, we can sometimes simplify radicals. You'll remember from algebra, chapter 6, that a square root sign is called a radical. It can be a cubed root, it can be a fourth root, but if it has a root sign in it, it's called a radical. And we can simplify radicals. There's another video, I will link that in the description. I have made another video about how to simplify radicals. But we'll do another brief summary of it here as well. So, What you want to do when you're simplifying radicals is you want to take what's inside the radical. So 147, and we want to see, is 147 divisible by any square? And when I say square, I mean 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on and so forth. We want to see, can I divide 147 by any of these numbers? Any of these perfect squares is what they're called. So let's try. Let's take 147 divided by 4. Oh, if I take 147 divided by 4, I get a decimal. So that doesn't work. I don't want decimals. What about if I take 147 divided by 9? Ooh, I get another decimal. I get 16.3333 repeating. That's not going to work either. 147 divided by 16. Still a decimal. 147 divided by 25. Still a decimal. 147 divided by 36. Ooh, still a decimal. 147 divided by 7 squared is 49. Hey! 147 divided by 49 is 3. This is good. This is good. Because this means that, and here, let me erase the perfect squares. We don't need those anymore. This means that I can write x equals the square root of 49 times 3. Because 49 times 3 is 147. That's what I discovered right here. 147 divided by 49 is 3. That means if I multiply 49 and 3 together, I get 147. Now, I can split these square roots, or these radicals. Remember, you can't do that. If we are adding, you absolutely cannot split them. You cannot do that. But if we're multiplying, you can. So this is good. Now, what is the square root of 49? Oh, 7 times the square root of 3. So, this is probably the answer that Big Ideas is going to want. If it says an approximate answer, well, there you go. You can take your approximate answer. If it says it wants an exact answer, then you'll give 7 times the square root of 3. And again, if this simplifying radicals went too fast for you, there is a link in the description to another video with lots more examples. Let's check and see if we were correct. A squared plus b squared equals c squared, x squared equals 147, and then they simplified the radical. 7 times the square root of 3. So, oh, we almost forgot. Oh, we forgot the second part of the question. Shame on me. Tell whether the side lengths form a Pythagorean triple. 7 times the square root of 3 is not an integer. Remember, integers are whole numbers, positive and negative, but the square root of 3 is not a whole number. It's like 1.69 yada yada or something like that. So, these side lengths do not form a Pythagorean triple. All right, one more example for today, and it is a real-life problem. So, the skyscrapers shown are connected by a skywalk. Ooh, so like a bridge between the two buildings. With support beams. So the support beams are right here. Use the Pythagorean theorem to approximate the length of each support beam. Approximate means that we can have a decimal answer. If we want an exact answer, no decimals. But if we want an approximate answer, we can take the decimal. So, first thing I'm going to do is I'm going to look at my diagram. We want to know the length of the support beam. So here are the support beams. X. So we want to find the length of the support beam, x. Notice I have a right angle up here in both of these corners. That makes sense. You wouldn't want your sky bridge drooping in some way. You would want it perfectly straight across. So the support beam is the hypotenuse, because it's perfectly, it's across from the right angle. Okay, then each of these sides are 23.26 meters, and each of the other sides is 47.57 meters. So, we know that a squared plus b squared equals c squared. The hypotenuse is c, and the other two sides are a and b. So we have 47.57 squared plus 23.26 squared equals x squared. Okay, we can put this into our calculator, 47.57 squared, and we can do this all at once. We can plug all of this in our calculator. Plus 23.26 squared is 2,803.9325 equals x squared. And now we can take, we can take the square root of both sides to get rid of that. And what do we get? We get approximately, remember we're going to use that squiggly equal sign, approximately 52.9521 blah blah blah. It doesn't say what to round to. It doesn't say to round to the nearest tenth, to the nearest hundredth. When in doubt, I like to round to the nearest hundredth, 2 decimal places. Because then if they wanted the nearest tenth, oh okay, it's not hard to round up from there. Okay? Ta-da! And there's the length of our support beam, because the support beam was x. And we found what x was. Yay! Let's check and see if we were correct. A squared plus b squared equals c squared. X is approximately 52.95. Oh, meters! We forgot our units. Oh my goodness. Meters, because everything else was in meters as well. Woohoo! We were correct. Alright, now is the time to assess your understanding of the learning target and the success criteria. Do you know what the Pythagorean theorem is? A squared plus b squared equals c squared when we have a right triangle. And can you use a squared plus b squared equals c squared to find the lengths of sides, hypotenuses, solve word problems? How are you feeling? Are you solid on it? Are you a 3? Are you a little iffy, like I think I got it but I need to try some more? Or are you like, I have no idea what's going on right now? No matter where you're at, it's all part of the learning process. So, ask questions, try the homework, help your friends, whatever stage you are at in the learning process, there is an appropriate action you can take. The practice problems for this video actually fit on 2 slides. We have some like example 1, some like example 2, and you guessed it, some like example 3. So, try these practice problems to assess your understanding, to practice the skills that you have learned in this video. And as always, we will end with a launch. Today's launch comes from Dr. Seuss, and he says, "You have brains in your head, you have feet in your shoes, you can steer yourself in any direction you choose." Now, when I first read this, I actually thought it sounded a little condescending. Like, you have brains in your head, you have feet, you can you can take care of yourself. I was like, oh, excuse me, Dr. Seuss, okay. And then I took a step back and I said, well, wait. This doesn't have to be condescending. This can be empowering. I have brains in my head. I have feet in my shoes. I can make my life what I want it to be. I can steer myself in any direction I choose. You choose where you want your life to go. You choose how you want your life to turn out. That doesn't mean that people aren't going to do crappy things and that you're not going to experience awful things. That doesn't mean any of that. But you get to decide, am I going to overcome these obstacles, Or am I going to let them define me? Am I going to push through when things get hard? Or am I going to give up? That you decide. No one else gets to decide that for you. You do. So, you have brains in your head, and you have feet in your shoes. What direction will you choose to steer yourself in? That is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thanks for being here. Thanks for watching. Bye.